So one of the things that Orsted's discovery showed us is that whenever you have moving current, you have a magnetic field that sets up. Today we're going to look at the hand rules for these magnetic fields that occur whenever you have moving current. Let's keep a couple of things in mind as we move forward. First of all, magnetic fields are vectors that point from the north to a south, and so when it comes to a permanent magnet, you can see how the magnetic fields of this magnet here go from the north pole of its on the right side to the south pole on the left. It's worth noting, though, that if you have two bar magnets, you get kind of a vector total or a overall magnetic field in this region in space because of both permanent magnets. So you still get this effect where the magnetic field lines go from north to south, but sometimes they'll go from the north of one bar magnet to the south of the other one. Now, this general rule that magnetic fields go from north to south on the outside of a magnet works fairly well for a bar magnet. Once you've seen a few of them, you can start to get an idea of the space around the bar magnet and the resulting magnetic field. But what about when we have moving charges? When we have moving charges, we have hand rules for the magnetic fields that occur. So really, you're going to learn in this course 3 different hand rules. We'll deal with the first 2 today. They're very conceptual. The third hand rule comes with a set of formulas as well, so we'll leave that for another lesson. But I'm going to summarize all the hand rules now. When we're done, you can go back and revisit this slide. But consider that we will learn 3 hand rules in the end. So the first hand rule is for a current carrying wire. So in this picture down here, we have a wire. It's the black piece here. If I highlight it, and so you have this wire here carrying current, and in the picture it's showing current traveling from the right to the left, and then we have a hand that's going to demonstrate the rule for predicting the magnetic field. Second hand rule is for a different situation. In this situation, we have a coil of wire. So in the picture that you see here, they show electron flow going through this wire here, up and around this coil. So we call this a solenoid or coil of wire. People recognize this as an electromagnet, really. And then the third hand rule, which we're not going to deal with in this lesson, but will come up, I just want to make you aware of it, is for current carrying wire that is in a magnetic field, or it can also be used for charged particles in a magnetic field. So as we move forward, consider that we're going to have 3 different hand rules. They are all necessary and they're unique, so don't try and mix them up. If you apply them strictly, the first hand rule for a single current carrying wire, use the second hand rule only for solenoids or coils of wire, and the third hand rule only for charged particles in magnetic fields or current carrying wires in magnetic fields. That's the first thing that you can do yourself a favor. Do not try and use these rules under different situations. One more thing before we move forward, you're going to see these hand rules. If you go on the internet and you Google hand rules, you're going to see a lot of different places teaching them, and they essentially say the same thing, but you have to be careful. Depending on whether or not you're talking about positive or negative charges, we use either the left or right hand. So when it comes to the hand rules, the left hand is whenever we're dealing with negative charges, and the right hand is whenever we're dealing with positive charges. All right, so keep that in mind. This is really important. And at first, I like to teach the left-hand rule because for the most part, we talk about charges moving through wires. And as you're probably aware, electrons are really the carriers of electrical current through wires. So I'll probably talk mostly about the left-hand rule, but it's really easy to change gears. Once you know the left-hand rule, we can talk about the right hand as if positive charges were flowing. Now, we know this doesn't really happen in wires, but you will see situations in which people talk about positive charges moving through wires. And definitely when we get away from wires, we can definitely have positive charges moving through other mediums like through water or through space or something like that. But for now, keep that in mind. When we talk about the hand rules, we can talk about them generally. Left hand is for negative charges, right hand is for positive charges. All right, so the first hand rule is called the wire grasp rule sometimes. And it reads something like this. If you grasp a current carrying wire with your thumb pointed in the direction of charge flow, your fingers will indicate the direction of the magnetic field around the wire. So this picture gives you an indication of how this works. So you can see the hand indicating the direction of electron flow, which is your thumb, the direction of the magnetic field lines, and they point with arrows. You can see the arrows on the fingers here. So here's the direction of the magnetic field on this finger. And so you kind of get the whole picture here, what's happening with the hands, and then they have a visualization here, what's really going on with the conductor. So magnetic field lines shown here, flow of electrons here, and then what your left hand would be doing to meet the conditions here. Again, thumb indicating the direction of electron flow. In this picture, it's from right to left, so the thumb's pointing to the left. And then your fingers will naturally grasp in the direction of the magnetic field. So you can see how the fingers are grasping in such a way to show this rotation around the wire that's consistent with what's being shown here, right? So we can see how the magnetic field in this region is indicated by the hand rule. Now it's easier to see this if you have kind of a visual for this. So let me show a clip from this video just to show you how to apply the hand rule for current carrying wires.
Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around a conductor with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately.
Might help if I demonstrated this for you. So I have a piece of PVC pipe right here, and I always find it easier. I know questions come at you from on a piece of paper, and they show pictures of wires and magnetic fields. This is really kind of a three-dimensional thing that goes on here. So sometimes it helps take something. I mean, if you're writing a test or something, you grab your pen, use that as the wire. I'm just going to use this because I can kind of label it. But imagine that this is a wire, and imagine that this wire has electrons flowing in it in this direction. All right, so they're flowing from right to the left-hand side. All right, so now I've labeled my PVC pipe to show the direction of electron flow. So I should be grabbing the pipe in such a way that my thumb points in the direction of the electron flow, and my fingers will wrap in the direction of the magnetic field. So you can see that at the top of the wire, the electrons will be coming out, becoming towards me, and in front of the wire, my fingers would be pointing up. So my magnetic field at the front of the wire is up, and then it goes into the page, we would say, if this was a page, or towards me, and then down when it gets to the back of the wire. So the magnetic field is really going in this direction here. So this is a really kind of kind of visualize it in your mind, but you can also get a sense if you kind of do it with a pen or something like that. So again, just make sure you grab with your thumb pointing in the direction of electron flow, and then your fingers will point in the direction of the magnetic field. So here's an image of what it could look like if you drew it on a page. You can see, in either one of these images, they indicate current using the letter I. We'll get used to that later on. But you can see how they show the flow of electrons in these wires kind of traveling from the bottom to the top, and then how your fingers would wrap around. Again, really kind of this, got to have a three-dimensional look at it. But in the end, if you use the image on the right, you can see how as the current flows basically up in the wire and your fingers wrap around. If we looked at a page or a cross section of the wire, you can see how the flow of the magnetic field could be described as like counterclockwise. Now, the second-hand rule is for a solenoid or a coil of wire. Basically says if you graft a solenoid, sometimes called a coil of wire, sometimes called, you'll hear me call it electromagnet a lot, with your fingers wrapping in the direction of the charge flow, your thumb will point, should be an R there, your thumb should point in the direction of the end that acts like the North Pole. So I know people want to kind of blend the first and second hand rules, but they're really independent of each other, two different situations, and what your thumb and your fingers end up doing are totally different as well. So there's no real connection between the first and second hand rule, so don't make that artificial. So you can see what happens here. It's changed the rules. Our fingers, now I see in this picture, the fingers are the direction of the electron flow, and then our thumb will indicate the direction of the magnetic field. So again, if you had this picture of this, you can imagine trying to work with that, try and wrap your hand around this thing. You can try and visualize it on a piece of paper. But again, if you were to just grab a pen and pretend that that pen were the section of wire that you're interested in, and there's coils of wire around it, then you would wrap your fingers in the direction of the current, or the electron flow in this case, and then your thumb should show you which side is the North Pole. Then once we establish that this side is the north and this side is the south, that allows us to draw the resulting magnetic field. So they would go from north all the way around, a little glitch there, to the south. Try that again. From the north all the way around to the south on the outside, and then return back in. Now, on permanent magnets, we always talk about the outside because really that's all that's going on. So we could indicate the direction in that direction. But now this thing is hollow. We can actually get inside here and take a look at what's happening to the magnetic field inside here, and we would see it would go this way. That's why we originally said, well, on the outside of a magnet goes from the north to the south, and then now we can see it coming back again inside of this thing. Really bad picture. I'll get a graphic here for you. All right, so here you go. Nice looking picture for us to look at. So you can see this one, you know, get used to seeing pictures kind of like this. We have a battery down here that's connected. And now this is, you know, I'm not going to go into the whole story of this, but a lot of people still insist on talking about current, I, as the flow of positive charges. So this picture clearly is showing the positive charge moving along here. And that current flows through the wire and around this way. So I always think of like a water slide or something like that. So we're pumping water through here, and the water flows through these wires all the way around, ends up coming out this way where we pump it back up again. So we can get a little practice here with changing gears and talking about the hand rule in terms of the right hand. If we're going to follow the positive charge, that's what we do. So we can follow this in this direction. So we would want to grasp this solenoid or this coil of wire in such a way that our fingers on the front point up, and then they go kind of into the page and around the back. And so when you're grabbing it on the back, so why don't you just take a pen right now, hold it in front of the screen, and take your right hand and grab the pen in such a way that it indicates that in front of the pen, your fingers would always be pointing up, and then behind it'll be pointing down. And I think you'll notice that when you're done, you find that your thumb points in this direction. So that means this is the North Pole and this is the South Pole. And now we can see why they have the magnetic fields drawn the way they do. It's because if this is the North Pole, they would swing around and come around to the South Pole and then back again in the middle. So that's kind of this second-hand rule allows us to predict. If we know the current, we can certainly predict where the North and South Pole are, and then we can draw the resulting magnetic field lines. Now you might say, oh, well, that works with the right hand. What if we wanted to use the left hand? Well, no problem. If you're following the left hand, then you're paying attention to which way electrons flow. Now electrons, I'll just highlight those in red, electrons would be flowing from the battery, from the negative terminal in the battery, in the opposite direction. So as the positive charges are moving in this direction, our negatives are going this way. So I'll invite you now. Imagine if you took your left hand and take a pen as if it's got a bunch of wires wrapped around it, and grab the pen in such a way now with your left hand that your fingers in front of the pen are pointed down. They're pointed up behind the pen, and you'll find that again, your thumb will point to the left side of the solenoid. So it doesn't really matter. They didn't have to tell us which charges to consider. We could consider either charge if you prefer your left hand, trace the path or the direction of the electrons to the solenoid. If you like your right hand, follow the path of the positive charges in the solenoid. Either one will work and they'll be consistent with each other. I just prefer using the left-hand rule because in reality, I think we all acknowledge that it's the electrons that are really carrying the current through this wire. All right, so here's a little check for understanding. This is an old exam item where it's kind of interesting when I like it in some ways. I don't like it in other ways, but electron flow in a loop of wire. So you can see that these arrows are supposed to indicate to us electron flow. So when you read questions, be careful. Are they talking about positive or negative charges, electrons, or the flow of positive charges? They sometimes call that conventional current, but here you won't hear much of that from me or from anybody in Alberta, Canada, but anyway, it's out there. You might see it. But if we consider this is the electron flow, so the electrons are flowing in this direction, so you can picture them as going kind of clockwise on this thing, and we want to predict. So instead of, because it's kind of changing and it goes in a circular format around these wires, you'll see this sometimes where they'll say, okay, here's point P. What is the magnetic field at point P? And you got these options. Is it into the page? Is it out of the page? Is it towards the left or is it towards the right? So I'll give you a chance. You can pause the video. You can take a look at that, and then I'll tell you what I think. So the first question, you're going to ask is, like, which hand rule should I use here? And this one's an interesting one because I really think you could probably use either of the first two hand rules. We could, if we wanted, just kind of ignore everything that's going on except this sectional wire that I've kind of outlined with my rectangle here. So if we ignore the rest of this and just thought of this as a single coil of wire, then the first hand rule would say, if I grasp this wire in this region down here, I'm going to grasp it down here, and I'm going to grasp it in such a way with my left hand that my thumb points down. All right, so I'm just going to write that in this region. Just check for yourself. Your thumb should be pointed down. All right, so you're grabbing that with your thumb pointing down. Now your fingers wrap. Now the question really is, which way would your fingers be pointing at this location right here? So if you grab it, you could probably just position your fingers in such a way that you can see that in order to kind of wrap your fingers around this wire, you'd have to put your fingers into this point right here. You'd have to cut a hole at this point right here and maybe a couple others for your fingers to go through. And if you cut holes in the page there, then you could grab this section of wire, this section of the page. But clearly, in my mind anyway, but I'll give you a second to confirm that, if you do this, the only possible result, and I have students that will tell me sometimes, oh, it doesn't work for me and I'm not getting the same answers as somebody else. If your hands have their thumbs in the right places and the fingers in the right places, you should have no problems with this. And so you're just applying the rule wrong if you're getting it wrong. So check it out for yourself. If you use the first hand rule with your thumb pointing down on this sectional wire, right, then your fingers have to kind of go into the page over here. So I'm going to go with A, into the page. Now, somebody might have said, well, that's really a wire loop. And so I can treat this as a coil of wire. It's a single coil, but it's still a coil of wire. Now, if I was going to apply that, it gets a little trickier, but it can be done. So if you wanted to do that, then you'd have to grab this wire, this time with the second hand rule. Remember, your fingers will point in the direction of electron flow. So take your left hand and grab the wire, or imagine that it could grab this loop, and your fingers are pointing in this clockwise direction. So put your hand in front of the screen right now, put your fingers from your left hand pointing in such a way that they show the electron flow around here. Now, what you're probably going to notice is your thumb is pointing right at you. So that means that the top of this wire, this is where it gets a little hard to kind of imagine, but the top of this wire is the north side. So the top of the page, the bottom of the page, or the back of the page might be the south side. And so it gets tricky, but then you can imagine, well, if on the top of the page it's north and the back of the page is the south, then I'll just draw out here as the north and back here is the south, and it's hard to see. But to me, this is where this gets hard. I mean, it's doable, but in this region, you would draw lines going from north to south, so they'd have to go into the page again to go from the front of the page to the back of the page. Again, which hand rule doesn't really matter. I find the first hand rule easier to explain, but you could really use both hand rules to establish the same answer here, that this thing is definitely got a magnetic field that is into the page. All right, here's another old test item. Describes a magnetic levitation or a maglev train floating above rails. And they accomplish this by putting a permanent magnet on the train and electromagnets in the rails. So again, take a second, pause the video, take a look at the information provided, and make a prediction. Which of the following designs would produce the greatest lift? All right, if you had a chance to pause it and think about it yourself and predict your answer, let's take a look at this. To create the greatest lift, we really actually have to show a couple of understandings here. Number one, to get lift, we have to have a repulsion between the electromagnet in the rail and the permanent magnets on the train. All right, so first thing we're looking for is we need to create a situation. If the permanent magnet has on the bottom a north, we need to create a situation in which we have another north at the top of the electromagnet. So I'm just going to sketch that in on each of my pictures, that the top, let me try that again. In this picture, to get repulsion, I need the north on top. For option B, I need a south on the top. For option C, I need a north on the top to repel the other north. And finally, for option D, I need a south. So the first thing we're going to ask is, which of our electromagnets is set up in such a way that we get the right pole on the top? If we get the wrong one, they'll be attracted and our magnetic levitation train will not levitate. It'll just get stuck to the rails. So I guess we can go through this somewhat in order. If I look at A, for example, electrons are flowing from the battery from the negative side around this way. So I'll indicate that with an arrow. So I need to grab this thing in such a way that my hand wraps around with the fingers in front pointing. Let me get a different color here. With my fingers pointing from left to right. When I do that, I actually end up with my north pole down at the bottom. Try it yourself, you'll see. Left hand, fingers are going in front of the electromagnet in front here, then into the page, and then on the back, they're going from right to left. So I end up grabbing it in such a way my thumb points here. So I'm going to rule out this one. This magnetic levitation train would not levitate. All right, so if you now notice, each of these batteries is connected the same way. So if A doesn't work, then I'm going to say C does not work either. And you can confirm that for yourself. But they create a situation where the north is actually not on top. The north is on the bottom. So we need to consider B and D. Looks like B and D, and you can confirm this for yourself. B and D, they work out because they will end up with north on the bottom, south on the top. So then the question becomes, if they both have a chance at levitating, the next keyword here is which one gives the greatest lift. Now, this isn't something we've officially talked about, but it is something that I think makes common sense. The difference between B and D now is this one has just a few coils, right? Whereas D has a whole bunch of coils. So when it comes to electromagnets and coils of wire, and we consider the number of coils, you got to consider that each coil has a little bit of a magnetic field. So as you add more coils, you're going to add a little bit more of a magnetic field. This is the whole reason why electromagnets use not just one coil, but a whole bunch. If you've ever taken apart a electric motor or any device that uses some sort of electromagnet, you'll see that they use usually really small wire and they wrap it a whole bunch of times, because for each wrap, you're getting one more magnet being created. So if you can, in this case, have what, one, two wraps here versus 1, 2, 3, 4, 5 wraps, you know, better to have the 5 wraps here than the 2 wraps here. So we'll eliminate that. I think I'm going with answer D. Why? Creates repulsion between the south and the south. The electromagnet south pole will repel the permanent magnet south pole, and more coils, more lift. Okay, so to summarize, I'm going to go back to the first slide. We haven't got here yet. We haven't got to our third hand rule. It's coming, and we'll deal with that when we have to. But for now, first hand rule, remember 2 things. When do we use it? For current carrying wires. And what does it look like? Our fingers will indicate the direction of the magnetic field. Our thumb indicates the direction of charge flow. Second hand rule. When do we use it? For coils of wire, for solenoids, for electromagnets. And how do we apply it? Well, if our thumb indicates the direction of the magnetic field, our fingers wrap in the direction of the electron flow. Takes a little bit of practice, like a lot of things. Some people pick it up really quick, some people take a little more time. So I'll provide you with a bit of practice as we move forward. But just know the third hand rule is probably the most commonly applied one, but definitely have to know the first and second hand rule. And to me, this is kind of like one of those skills. Once you build it and you have it, should be able to handle pretty much any question that comes with these hand rules.